Semiconductors and the invention of transistors. Shared electrons in metals and semiconductors. Conductors such as metals consist of positive metal ions in a sea of free delocalized electrons. Delocalized electrons just means that the electrons are not associated to any positive ion in particular. Although the electrons are all moving in random directions, constantly colliding with each other and changing velocity, there is no net movement. Only once an electric field is applied do the electrons move in a net direction. The flow of electrons will move in the opposite direction of conventional current. This means that electrons will flow from positive to negative. In semiconductors, there are only some free electrons. These few electrons have enough energy at room temperature to jump the energy gap and move freely. This means that there too would be less free electrons if an electric field was then applied. Difference between conductors, insulators, and semiconductors. Within atoms, there are various band levels. The valence band is the outmost band with the highest energy. The conduction band is the one that allows the free transfer of electrons between neighbor atoms. In between the valence and conduction bands lies an energy gap which can change the willingness of an electron to travel from the valence band to the conduction band. An electron cannot, however, be in the energy gap. In conductors, the conduction band is very close, often overlapping the valence band. Therefore, the electrons can easily jump the energy zone and enter the conduction band for the flow of electric current. This means electrons have very low electrical resistance. In semiconductors, the energy gap is small, allowing for some electrons to flow from the valence band to the conduction band at room temperature. By increasing the thermal energy in semiconductors, aka increasing the temperature, it provides the electrons with more energy, causing more electrons to be able to jump the energy gap. Therefore, the resistivity of semiconductors is dependent on the temperature of the semiconductor. In insulators, the energy gap is quite large and would need a large amount of energy to send the electron from the valence band to the conduction band and therefore to conduct electricity. This means that the electrical resistance is high, allowing low amounts of electrical conductivity. Relative number of free electrons. Doping a semiconductor is the addition of an external atom in the pure crystal lattice of a semiconductor. An intrinsic semiconductor is a semiconductor that occurs naturally without the process of adding an external atom to the pure crystal lattice of the semiconductor. An extrinsic semiconductor is a semiconductor that doesn't occur naturally, and this is due to the addition of an external atom in the crystal lattice. The two types of extrinsic semiconductors are p and n-type semiconductors. Absence of electrons as holes. In substances, elements which have a nearly full out-of-valence shell, the absence of an electron is known as a hole. When a potential difference is applied, other electrons are attracted to the positive charge carrier hole and takes up its space in the positive direction, whereas the positive charge carrier hole will move towards the negative difference. Where the previous electron was, there is now a positive charge carrier hole. This process continues indefinitely. Therefore, holes in valence shells of atoms and electrons help the flow and carry of current. Doping a semiconductor and changing its properties. Doping a semiconductor is the addition of an external atom in the pure crystal lattice of a semiconductor. An intrinsic semiconductor is something that occurs naturally without the process of adding an external atom to the pure crystal lattice of the semiconductor. An extrinsic semiconductor is a semiconductor that doesn't occur naturally, and this is due to the addition of an external atom in the crystal lattice. The two types of extrinsic semiconductors are p and n-type semiconductors. P-type semiconductors. P-type semiconductors are made when a group 4 element is doped with a group 3 element. Group 4 elements have 4 electrons in the valence shell, whereas group 3 elements have 3 electrons in its valence shell. This change in structure will create positively charged holes in the silicon lattice. The P in P-type stands for positive due to the addition of positively charged holes. N-type semiconductors. N-type semiconductors is when a group 4 element is doped with a group 5 element. Group 5 elements have 5 electrons in its valence shell, meaning there will be an extra electron. The N in N-type stands for negative due to the addition of negatively charged electrons. It is important to note that although they are called negative and positive types, they are neither actually negatively or positively charged. Difference between solid-state and thermionic devices. Thermionic devices and solid-state devices control the current flow, convert AC to DC, or switch current flow on or off. Thermionic diodes are devices which allow current to flow in only one direction. They utilize heat filaments and terminals set in glass vacuum tubes to act as an amplifier. The filament in the vacuum glass tube is heated by an electric current to high temperatures, causing it to liberate electrons and act as a cathode. These electrons are then accelerated towards the anode by a high potential difference. Solid-state devices are made from a combination of p and n-type semiconductors. This combination allows current to flow in only one direction. Electrons must move across the junction from the n-type semiconductor, neutralizing available holes in the p-type. Improved transistor technology. Thermionic devices had many problems. This led scientists to set out and discover new technologies. In 1948, germanium was used in the transistor for the first time. This was a major breakthrough and has led to further technological advancements itself. The transistor is small, long-lasting, and reliable. It was much more efficient than thermionic devices and advantageous in many ways. However, due to germanium having a number of problems, it became necessary to develop more reliable semiconductors. This led on to research of silicon production and eventually allowing the creation of silicon transistors, which overcame shortcomings of germanium use. Why did solid-state devices replace thermionic devices? Thermionic devices are much bigger and therefore appliances were more bulkier than solid-state devices. Solid-state devices are really small, allowing for the miniaturization of complex circuits. The reliability of thermionic devices were very unreliable, as heated filaments would often break down and stop functioning. Solid-state devices were very reliable and did not need replacement or maintenance as often as thermionic devices. Thermionic devices were very fragile. On the other hand, solid-state devices were very robust and could withstand some degree of damage. Thermionic devices require more electrical energy and produce large amounts of heat. Since large amounts of electrical energy is dissipated as heat, thermionic devices are often very insufficient. Solid-state devices are energy efficient and operate instantly. Thermionic devices are expensive, while solid-state are cheap and easy to make.